Hello everyone, I'm Yixian from Peking University. I'm glad to present our work Propagation with local structure and its application in program analysis. In program analysis, probability reasoning becomes an effective way to represent non-deterministic properties and relationships. It introduces several random variables to represent the probability of a program element's property. For example, let random variable x represent statement A being incorrect, and y represent statement B raising an exception. In addition, introduce some probability constraints among random variables to model the relationships between these probabilities. For example, let the conditional probabilities between the relationship to describe how y is affected by x. Therefore, in order to represent the multi-dimensional discrete probability model introduced by program analysis, it usually uses a probability graphical model. For example, the directed Bayesian networks and undirected vector graphs. It combines numerous local probability constraints into a multi-dimensional joint probability distribution. And the key inference problem is to obtain the marginal probability distribution. For example, SmartIFL and Bingo are program analysis applications with probability reasoning. SmartIFL focuses on photo localization, aiming to find the location of faulty program elements. It introduces random variables to represent the correctness of program elements and transform program semantics into probability constraints between random variables. Bingo is a static analysis approach to find alarm reports. It extends traditional logical program analysis with probabilistic constraints to quantify each logical deduction rule with a probability and deduce a confidence score for each alarm with user feedback. One of the major problems in these works is the efficiency of the inference algorithm. Exact algorithms typically cannot handle large graphs with cycles. Therefore, loopy-based propagation becomes the practical approximate inference algorithm. However, a single loopy-BP message update requires enumerating all possible assignments to the variables in a factor, which can also affect the efficiency. To solve this problem, our key insight is to exploit local structures in loopy-BP. Many assignments with the same probability value can be grouped to avoid expositional enumeration. For example, the widely used probabilistic Horn clauses indicate that if all x on the left are true, there is a probability p to deduce y. We can use local structures to make efficient inference on probabilistic Horn clauses. Now, we use a factor graph as an example to demonstrate how loopy BP works. In the graph, each cycle represents a random variable, and each square represents a factor, corresponding to a factor function describing the probability constraints between the random variables connected with the factor. Loopy BP iteratively sends messages between random variables and factors, updating them with the messages from the previous round. Each message value can be viewed as a temporary marginal probability distribution of corresponding variable. These two formulas demonstrate how messages are sent between variables and factors. Specifically, this message from a variable sent to a factor is the product of other messages it receives. For example, mu v1 to f3 is mu f1 to v1 times mu f2 to v1. Next, for a factor to a variable, it uses messages from other variables as their temporary marginal probabilities to sum over the factor function to calculate the message. For example, mu f3 to v2 is the sum over variable x1 on the factor function f3 times mu v1 to f3. This formula represents the main calculation process of loopy BP, also known as sum product, which refers to this process of this product and this sum. Now, let's assume a factor is associated with n variables, and all variables are binary random variables. There will be O 2 to n terms in this sum, and we have to enumerate all variables assignments over the n variables except the variable receiving the message. And each term needs O(n) products. Thus, this process leads to exponential complexity. Well, this isn't a problem when n is small, but it can negatively impact the efficiency of loopBBP if there are many factors with large n. To address this issue, the key insight of a paper is to exploit the local structure of factors. This can be understood as follows. In program analysis, different variable assignments often result in the same factor values, allowing us to avoid exponential enumeration. Here is an example from SmartFL. It builds the example factor from this statement to represent the correctness between the result and its sources. In this example, if V0 to V6 are true, the result V7 is true. If not, the conditional probability is set to be 0.01. We can also write it as the factor function like this. In this factor function, if V0 to V7 are all 1, the result is 1, and so on. In this case, let V0 to V6 be the set V. A loopBBP message value from the factor to V7 is calculated using this expression. To exploit local structures, we first need to introduce a series of indicator functions GCX to represent atomic constraint for a random variable. If the input x equals to c, GCX is 1, otherwise GCX is 0. Then we can introduce several condition functions G1, G2, G3, and G4 to represent the conditions in the factor function. Each condition represents a term in the factor function. As a result, we can transform the factor function into this, and then transform it into this aggregate expression because these four terms are mutually exclusive. After expanding the conditions back into the indicator function, we can simplify the function factor into a linear algebraic expression as equation 2. Now we have the factor function expression 2 in linear representation. Substituting it back into expression 1 of the loopBBP message calculation, we can get the following formula. Notice that G01 should be 0. We can further simplify this formula to its green form, representing in a linear computed expression for loopBBP messages. Our main experiment is based on two program analysis applications with loopBBP, SmartFL and Bingo. Both applications' probabilistic model primarily consists of probabilistic Horn process, and we compare the computation time of their original loopBBP with our optimized version. For SmartFL, we can see it has a good acceleration rate. The average acceleration rate is 5.11 and the median is 2.77. For Bingo, this picture shows the number of true alarms versus the time cost in 8 different projects. In each project, we executed the optimized loopBBP and the original loopBBP 3 times each, and the results are represented by solid lines and dashed lines. For the first 4 projects, the optimized loopBBP has 2.1 average accession rate to find all true alarms. For the last 4 programs, Bingo finds 2.76 times true alarm before timeout with optimized loopBBP. Finally, here are the main contributions. Our tools and data are in this GitHub link. You are also welcome to scan this QR code to watch a detailed video. Thank you.